So everyone, we've got a new instructor today, John Jackson. I'll let him introduce himself. And this is ML Topics 1. We'll have a different topic next week. And the third session, we're debating the topics on that one, but it will be machine learning related though. So let me hand it to John Jackson.
Hey, how's everybody doing? Thanks for joining. Quick background on me: for last couple decades at this point, I've been a tech entrepreneur, have built and sold a number of companies. Got involved with AKF about 2 years ago or so, which has just been absolutely fantastic to get a chance to dive in. I've been involved with AI machine learning for probably close to 10 years of that period. I'm currently actually through AKF. I've spent about the last 6 months, and I'm currently interim CTO for a AI biotech company that is focused on using AI for preclinical drug discovery. So it's been absolutely fantastic to dive into one of the most complicated domains, using some of the coolest, probably the most complicated tech out there to get these answers in place. Clients are some of the largest pharma in the world, so it's been very cool. We're gonna, for this session, probably narrow that down a little bit and start to talk specifically about AI models. So let me go through here. So get over. All right. So we're going to focus this session on an intro to AI generally and AI models. So the purpose of this is to give some background on a lot of the terminology that you probably have heard, a lot of the understanding of what some of these models are, from initial models up to generative AI. And part of the reason this is important, just to set the context as we get in, all the hype is around generative AI, variations of that, agentic AI, multi-AI, retrieval augmented generation. We'll touch on some different points of those, but these are huge models. And part of the reason that they get so much attention is that they are very easy to work with. They are also very expensive. And so one of the challenges that in my current role that we are constantly balancing is the ease that we can get questions answered with generative AI. Also the non-deterministic nature of it, the fact that the answer isn't always the same coming out. If you think about it, if you ask 100 scientists the same question, you may get most of the time fundamentally the correct answer, the correct information, but it's going to be phrased differently. It's going to have a different nuance to it. And so that can be very hard to work with, particularly when you're trying to do high speed, high volume. And so many of these sort of fundamental models that have been around for decades longer than generative AI are still the right tool for many tasks, particularly more focused, higher volume tasks where either more precision in a certain answer or just simply cost effectiveness at volume, at scale, are factors. So let's kind of crack open the history books and go back into what some of these underlying models are. And to start there, let's talk about the abbreviation. Most of you probably familiar with the nuances between those, the differences, but artificial intelligence is broadly any technology that enables machines to simulate human intelligence, problem solving, learning, decision making. Machine learning focuses on algorithms that learn from data and then are able to make predictions and improve over time. And so fundamentally, if we think about it, a thermostat is probably a version of artificial intelligence, right? It is making a decision, simulating when to turn the air conditioning on or off by monitoring the temperature with a very simple decision rule of, if it exceeds this temperature, turn the air conditioning on. If the temperature falls below this point, turn the air conditioning off. It's reasonably dumb, but it does a great job of keeping the air conditioning turning on and off as the house temperature changes. Machine learning is more like the smart Nest thermostats that actually start with that premise, but they monitor the temperature of your house and they turn the air conditioning. And a great example here with machine learning. So I live in an old has radiators, right? And so we have a boiler in the basement, we have radiators. And so what happens when you set the temperature for heat to 69 degrees, and temperature in the house, or not even in the house, in that spot right by that thermostat, drops below 69 degrees. Well, it fires the boiler up. It floods all of these pipes throughout the house and all these metal radiators with hot water. The temperature gets up to 69. It turns the boiler off, but the house is still filled with hot water through all the pipes, through all the radiators, and that heat dissipates into the house over the course of the next 20 minutes or so. And so the house actually goes reasonably above 69 degrees because it stopped it at 69, but the heat keeps coming in. And then at some point it cools back down, it gets below. And so it would do this swing. So a traditional thermostat, artificial intelligence, would continually swing the temperature, probably in a 5 or 6 degree band, as it worked it out. And it would only trigger when that temperature threshold were crossed. We have a Nest thermostat in that spot, and it begins to learn the fact that when it turns the heat on, the temperature radiates for a while. And so it actually learns to turn it on and turn it off ahead. It knows that if it turns it on for just a little bit, it will actually learn that the temperature will keep going up for a while before dropping. And so it optimizes, and over the course of about 3 or 4 months, we have no temperature swings in the house. It has learned the way the house and our radiator and our boilers work, and it optimizes it and it keeps it almost exactly at 69 by playing around with when it turns it on and off. Fundamentally different approaches, much more powerful. So when we say AI ML, that's a very long example of what we're getting to. So when we talk about ML, there are a couple different kinds of learning, right, at the core, and you can get a PhD in this stuff. So we're oversimplifying it. These are large buckets, but supervised and unsupervised learning, right? Supervised learning, effectively, there's an answer, and we're trying to reproduce that answer. And so we work with labeled data sets to train algorithms to classify or predict or whatever it is. But effectively, we're trying to train it to reproduce the same answer with variable inputs and get close to the right answer over time and at scale. And so it receives direct feedback. And we'll talk a little bit later about how some of this training works, but it receives feedback to understand the correlation between the inputs and the outputs. And it gets more complicated with multiple inputs, but fundamentally we've got an input. There's some correlation, we believe, between the input and an output, and then we train it to try to predict the output. And so examples of this are spam detection, right? We label 1 million emails as spam, and we have 1 million that we don't think are spam, and we keep training it until it reasonably accurately detects the spam in our training set and the not spam in our training set. And then we start running other models through it, and we hopefully have some feedback loop where somebody says, flag something as spam, and we can fold that in and we can adjust. But we're supervised learning. We're giving it a set of answers and trying to train it to reproduce those answers. So image recognition, sales forecasting, weather forecasting, all of those kinds of things. So often if you're doing detection, classification, forecasting, things like that, you're probably in a supervised learning category. Unsupervised learning gets more interesting because we don't necessarily know the correlation. We don't have an answer. We're trying to determine and segment patterns. So in this case, we're asking the machine learning system to look at the data and try to identify patterns that may be in there on its own. And then once that's identified, we can then try to do predictive work on that. And so a good example here can be customer segmentation, right? So we throw all our customers in, we throw a whole bunch of attributes about our customers in and set it to work. And what we're hoping is that we come out and the model can begin to find correlations between attributes of the customers that segment them. Like you never really understood, for example, that customers in Cleveland, Ohio, who happen to drive Toyota Prius are likely to also subscribe to The Economist, right? And so like would take you forever to sift through millions of customers to find these correlations, but if you can start to do that, and so very classic examples of this all through advertising, social networks, YouTube, anywhere else where we're trying to segment customers and get that. Another good example in this case is anomaly detection, right? It's hard to train. If, for example, a classic example here is if you are trying to find out whether do quality testing on an engine or a car or something very complicated, you can set all different parameters going, well, what's the temperature? What's the RPMs that we're hitting? All these different components. What's the measurement of oxygen that's still being emitted in the exhaust, and a million different things that we may want to measure. But there's a lot of correlation or relationship between those. And so it can be very hard to create a list from a supervised setting that says, well, if the temperature exceeds this number, the engine isn't performing well, because it may be exceeding that number at an RPM that's in excess of what we should ever be driving. And so the engine is operating normally for what we're doing. So you can create these boundaries that go, this is what normal looks like. We've got 1,000 engines that are normal. Here's what their outputs look like and the relationships between them all, and start to look for anomaly detection. So what you're actually asking is, I'm not looking for good engines. I'm trying to detect if an engine is performing outside the range of what is normal for the engines that we've been looking at that we think are normal. And so that is a form of unsupervised learning that is used constantly. It's one of the most popular forms. So now we've talked about AI ML, we've talked about supervised and unsupervised learning. Then the next sort of split here is predictive and generative, right? Predictive is trying to forecast something based on input. And we'll talk about some of these different types of linear regression and decision boundaries and even neural networks. I'm sure you've heard a lot of hype, particularly prior to generative AI, about neural networks. But these are all predictive. You're taking a bunch of inputs and you're trying to predict an output. Generative AI is different. We're actually trying to create new content or information or data based on learned patterns. And so in these cases, some examples are stable diffusion, large language models, and importantly, extending off of large language models, the GPT that allow us to do this. So we'll get into kind of the differences between all of those, but when you're looking at your toolkit and what's available for you as you try to integrate, these are sort of the large buckets. And so when you're making these decisions, the reason we went through these different sort of binary classifications here is when you're trying to figure out the right tool, in addition to looking at cost and data volume and speed and response times and all of that, you're going to kind of ask these questions. Do I have a lot of training data that I can label? Do I have an answer? Or do I just have a bunch of data and I need to figure out what's going on? Going back, so that basically, am I trying to learn what's happening, or can I just define a rule? If I need to learn, do I have data that is labeled that I can give it a bunch of things and test the answer right or wrong, or do I need to detect patterns? And then am I trying to predict something, or am I actually trying to create something new? And so those are sort of the flows that you'll go through as you're looking. So we're going back to probably the oldest form of machine learning that we've got, which is linear regression. And so this may be painful flashbacks for folks that didn't like math in school, but what was interesting here for me, none of this stuff made sense to me until I started to apply it in the context of machine learning. And then it was like this light bulb went off, and stuff people have been doing for hundreds of years at least, with pencil and paper, quill and parchment, however they were doing it. These are still the foundations of how all of this works. And these are really good tools. And so what happens with linear regression is we're basically trying to create a line that cuts through the center of our plotted data, right? And the reason for that is prediction. And in many cases, this is close to all you need to get some really good answers. And so this example here in this chart is just a plot of house size in square feet versus price in a given market. And we scatter it out all over the place and you try to identify a line that cuts relatively through the middle of it. And so then if we look and we say, well, for a 3,000 square foot house, we would think this is probably somewhere around $450,000, right? Because that's where the line is. Is it going to be exactly accurate? Absolutely not. There's only, in this whole thing, maybe 2 or 3 cases where the line is relatively over an exact dot that we have. And we can see as we get up into really large square foot houses, the model starts to fall apart. And so understanding some of those constraints is important as you kind of test. But we have a pretty good run here from what I presume is a 500 square foot condo up to a 2,500 square foot house. We're not going to be horribly far off here if we use this line. But we can go to the next, which gets into the math that really gives people kind of makes them shudder when they look at it. So what I never understood back in algebra days was why we had the x itself, x squared, x cubed, as far as we want to go, right? The reason for that is to shape the line. I wish somebody had just told me this back in whatever it was, 8th, 9th grade, when I was taking these classes. It's just to shape the line. And the reason for it is that the pattern that we've got might not be a straight line. It may follow some bit of curving as we go through. And so if you try to cut a straight line through curved plot data, you're going to be off at different points as you go through. And the number of curves that you get is based on how many representations of x you have, x and x squared, x squared, x cubed. It has nothing to do with the squared or the cube. That gets canceled out by the weight that you apply against it. It is just to isolate that this weight applies differently than this weight, and this weight applies differently than this weight. And the result of that is basically, if you have x to no power, we just have our bias, we have a straight horizontal line. If we add x once, we can tilt our line. We have a slope to our line. If we add x again and we square it to keep it operating separately from this x, we get one curve, and so on. If it's cubed, we have 2 curves, 3 curves. So we can get incredibly complicated line shapes by extending out the number of polynomials that we have. And so when you go down this road, if your data is reasonably clustering at all, this approach works well. There are great ways to train it to find what these polynomials should be, these expressions should be, and you're off to the races. And they run for fractions of a cent. They run in just Python. They're stupidly cheap to run. They're not hard to train. And they perform in single-digit milliseconds. And so if you have millions of data points that you need to process going through, this is a really good approach to do that. And as you go into this just with a slight twist, you can move regression, polynomial regression in most cases, outside of just prediction, which is where are we on the point? For a given x, what is likely our y, right? Into classification. And the way that you do that is you try to cut through. So in this case, let's say that the green are looking at test results, right? And we've got, based on a test result, we've got a certain elevation of a protein in a blood sample. And based on the elevation of that protein, we have a correlation as to whether we believe the person has cancer or not, right? Simple kind of thing. Or this is what you would do in any flu test, COVID test, any of this kind of stuff. And you would sit here and you would try to correlate, you cluster this, and we go, in this first one, all of our positives, I guess we'll call it for green. I feel like red should be they have cancer, right? But so we'll say the people who don't have cancer seem to be clustered in this set of values. Outliers outside those values, we feel might have cancer, right? So we try to create a formula that establishes a line. And so instead of going, and in the other case, we see the curved polynomial there, it's got 3 curves, so it is to the 4th power, basically. And it cuts through and basically shapes it, and we go, well, if they're below the line, we can classify it as no cancer. Above the line, we think they might have cancer. There are some false positives above, there are some false negatives below, but generally, we're in pretty good shape with that shape, similar with the other. So suddenly we've taken a forecasting model and used basically the same technology, the same expressions, and started to turn it into classification. And this is where things like spam classification and that got started. It was, well, if we see this stuff, do we think this is spam or not spam? Is this a swear word or not a swear word, right? And we can do pretty complicated classification based on these. And so that, again, that it's lightning fast, relatively easy to train if you have data, right? So this all falls in the supervised category. But if you meet these, this is a really good way to go. The way we train it is something called gradient descent. And these are algorithms that you will not have to learn. There are plenty of tools to help you with this and people to help. But basically, we just pick a random spot and we keep walking downhill, trying to get our error lower and lower as we go down the model. And so we make a prediction randomly. That prediction we test against our training data. It's wrong. We go, how much is it wrong? And we make adjustments and we go, is it more wrong this way or less wrong this way? And if it's less wrong, we make an adjustment and we keep working our way down till we hit the most accurate we think we can get in the shape that we're working in. And so then we jump up to what was probably one of the biggest breakthroughs that led to where we are today, which is neural networks. Fundamentally, every one of these layer steps, these interrelationships, is a polynomial expression. So we're still building on what we had before. We're just connecting a crazy number of these together to try to get to, in this case, a classification. Is it A or is it B? I have 3 inputs. We run them through a bunch of weights in this hidden layer, and we try to predict input or output. So examples here could be like, is the road going to be icy, right? Fair example, right? Well, how much sunlight is there, right? Because that can warm the asphalt separately from the air temperature. What's the air temperature? Is it above or below freezing? How much rain have we had in the last, I don't know, hour, day, whatever we want, right? So those could be 3 things, like how much sun is there? Is it sunny? Is it cold? Is it wet? Right? But different combinations of sunny, cold, and wet are going to go into the road is likely icy or not icy. And so this stuff is actually going on when in your car, based on what it's sensing in the way your wheels move and temperature sensors and what time it is and a whole bunch of stuff that many more input layers and a lot more hidden output layers determine whether the little icy road sign light gets flashed up in your car. And we can get incredibly complicated with this. But the core thing is that we have weights that get assigned, and we basically run some version of those polynomial expressions through here. So starting to get to fun examples are handwriting recognition. And there are classes online. If you have any interest in this stuff, there are tons of great classes that can go as deep as like the Stanford Machine Learning course, up to just find some good YouTube videos or whatever that walk through it. But this is one of the first neural networks that I ever built was for handwriting recognition. And it was amazing to see it actually start to work. And what you realize as you're doing it is no part of this involves anything that you couldn't do on pencil and paper or with a calculator. It's just at a scale that you never could execute it and get through one, let alone enough to train it. So it is the advances in computational power over the last few decades that have gotten us to the point that things fundamentally that we knew how to do, certainly in the 60s, most of this stuff was invented theoretically, tested at some level. Elements of it go back centuries, but we never had the computational power to run it at scale. And so that's the real breakthrough, is that we have Moore's law has caught up to a point where we actually can execute this stuff at scales that were unimaginable. The underlying methodology is basically high school math at some level. And we're obviously oversimplifying it because there's some absolutely brilliant algorithms that have been written to help shortcut this stuff. But so effectively, what's happening here, we take a snippet of handwriting. The first thing you have to do is you have to standardize it. So I think this is like 28 by 28 pixels or something like that, whatever the square root of 784 is, which I don't feel like calculating. We turn it black and white, right? So the colors don't matter. We identify the pixels, and we basically determine the lightness or darkness of the pixel, and we normalize it to between 0 and 1. So if it's all black, it's 0. If it's all white, it's 1. And if it's gray, it's somewhere between 0 and 1. And we put information in an array vector of 784 measurements of 0 to 1, representing each pixel. And then we basically train it by going, we take thousands, potentially millions of samples of these, and we put in the values, and we put random weights in, and you'll see this pixel is correlated to every single one of these nodes, right? And vice versa. And we have a weight. So this pixel impacts this node by this amount, right? So we just multiply 0 by some amount, 0.2 by some amount, and we do that for each one. And you just start randomly. So if you think of 784 times 9, right? That's how many weights we've got at every single one of these things. And we do it randomly. And it's going to come out, and we see which one of these outputs gets the highest answer, right? So these are all going to be rated from 0 to 1. And we're going to go, well, which one of these is closest to 1? First time through, maybe it'll be 3. We'll go, no, it should have been 8. What was our error going back? And we'll adjust these weights a little bit, and we'll solve for that one. And if you ran that same image back through again, you're probably going to get 8. But you're going to take another image, which is different, and you're going to run that one through. And even if you look at it and it's 8, it's probably not going to come through as 8, but maybe it'll come through as 6 at some point, which is close to 8. And you tweak it, and you keep doing that on millions and millions. And there are automated systems for running those. And we'll pop up here for a second. It's called back propagation, and it looks crazy. It's actually way simpler than it looks. But effectively, we're running the system through, we get an answer, we find out with a cost function how wrong we are, and we allocate that error back through, and we try it again. And we just keep doing that, tuning and tuning and tuning and tuning, and you get to your answer. All of this math could be done on pencil and paper. None of it is that individually complicated. It's just a lot of it. Deep neural networks for much harder problems, the trick is you just go through multiple hidden layers. Back to our example of ice, you may find that there's more of a correlation between temperature and how much rain we've had than there is between how much rain we've had and how sunny it is, right? There is probably a correlation, but the correlation requires some input from temperature. And so you can end up getting much more complicated, nuanced relationship. Think of it as those curves in the polynomial, but in multi-dimensional space. It lets us get more shapes every time we add another layer in order to get more complicated in what we're doing. And so we talked through this, and so it's just a computation question. It's how long it takes to train it, how much data you have. If you don't have enough data to get to this level of nuance, if you only have 3 examples of handwriting, you're not going to be able to train this. You need thousands at least, probably, right? And so this becomes an issue. Let me go back here for a second. The other thing that we got, saying back propagation was really 100%. Mastering this, the ability to allocate the cost function back over, was a massive breakthrough that unlocked pretty much everything that came after it. And it partly just required the computational power that we've got. One of the things that I want to point out as we're going through this is you'll start to make decisions at this point. One of the other factors that you're going to have is, do I have enough data in order to train any of these? And if you don't, then we start to move into LLMs and generative AI for reasons that we'll get into. But if you do have the data, if you can run these systems through, you're going to need to do it at volume, you very likely will want to explore some of these first stage models that we're looking at that are more in the predictive realm. Let's get up here. Great video here. I'm sure this can get shared with you. It's a YouTube video, 3 blue, 1 brown, absolute masterpiece. These guys, everything they do around math is like, if you're interested in any part, or if any part of math never made sense to you, or if you have kids that are going through taking calculus or algebra or something, go to 3 blue, 1 brown, find the videos on them, watch them yourselves, have your kids watch them. There will be this moment where things just click in hundreds of videos that they do. Specifically for backpropagation, it is an absolute masterpiece for understanding how these systems work. So highly encourage you to take a little time and watch the 3 blue, 1 brown backpropagation video if you have any interest. So just focused on time, make sure we've got some time for questions as well, and certainly pop them in the chat as we're going. So, okay, we spent a long time getting ourselves from artificial intelligence to machine learning to neural networks, backpropagation being a key part of that. The next major breakthrough are the generative AI models, right? So now we're not just predicting, forecasting something, we're actually trying to create something new. And so these are built on neural network architectures, but there's another element to them. And so again, the bottom thing here, neural networks particularly are good at complex, wide range of tasks, classification, prediction, pattern recognition. Generative AI moves into creating something more complicated. The one note that I wanted to add prior to jumping into this, and I knew I had a point I wanted to make. You might go, why do you not go all the way? If you have the training data and you have the power, the compute power, why wouldn't you go as complicated as you can? Why wouldn't you add 50 hidden layers here, or 1,000 nodes, or if we go all the way back up, why wouldn't we go to 100 polynomials here for trying to get to some kind of decision classification? Because obviously we've got dots that aren't right. And so we could probably get a better thing that like cut through here and cut out and maybe tucked up and put that around there and got the little dots going. At some point, you end up with what's called overfitting. And the model is no longer good for predicting anything other than the training data that it was sent. It will struggle with new data that it wasn't trained on because it's overfit, it's too convoluted to solve for the specific data that it has. And so you'll find you're going to need to resist the temptation if you go down these roads to overfit, to overcomplicate the models. You're looking for a reasonably generic, basically you define acceptable error rates and you're going to work to improve them, but you always have to be testing against new data. So often, like for example, you'll take half of your data set, you'll train on it, then you'll test against the other half of your labeled data so that you can test that you're not overfitting. And often what you'll find is if you get too complicated, you test on the first half of your labeled data, you get it doing really well, you try the second half of your labeled data that you didn't train on, and it crashes because you overfit. And then you actually have to dial back the complexity of the model for that. So, okay, back to generative AI, moving into the more fun stuff. This was crazy when I started to dive into stable diffusion, right? So when we think about the types of generative AI, there are LLMs that focus on language, there are transformer models that focus on chains of prediction, right? And we'll talk about both of those, and they often work together. But one of the cool outliers is stable diffusion. And so this is how all of these cool image sites, ChatGPT images, and how all these work. And so what they do is they get access to millions of images that are classified in some way that say this is a cat, he's on a counter, he's got black and white spots or patches, he's in a kitchen, you just label everything you can label about it, right? And then what they do is they introduce noise. So cat with white brown patches in a kitchen. That's the label. And so that gets input as part of your parameters that came in when we've looked at all of that. And then they introduce noise. And they say, if I give you, the second image is probably about 10% noise. If I give you this image, turn it back into the the original picture. And they keep training it because you can measure that. You can identify a cost function. You can propagate that cost function back through the training with back propagation, and you train it and you work it until you give it an image with 10% noise and the description, and you end up back with the original picture exactly. Then you do 20% noise and you keep tuning it. Then you keep going and you do that iteratively until you give it 100% noise. Give me an image with cat with white and brown patches in a kitchen. And it comes back, and you train it to come back to this image. And then you do another one and you do something totally different. You do a frog on a pond, you do a motorcycle going down the highway, and you do millions and millions on the same model. And you keep training it until it can reproduce each one of these images back to the original based on its description. And if you gave it another cat with white and brown patches in a kitchen that was different, it may come somewhere between those two, right? Because you're training it on both, and you work to get it back. The outcome of that, when you do that at high enough scale with enough different types of images and enough descriptions, is that you actually can start to generate new things. If it's done enough back porches and it's done enough black cats, you could say, give me a black cat on a back porch, even though it was never trained on that, and it will produce that image. But it's this diffusion, so it's stable diffusion. We stably increase the noise levels to get us back to this. Just absolutely fascinating sort of component of generative AI, and a way that you can go down. You can do this with not just limited to images, and video is basically chains of images where you're going together and you use the other ones as input as well. But you can do this for sound, for audio, for all kinds of things. And so it's anywhere that you've got the ability to basically slowly introduce noise, 15-minute time check, we'll keep moving. Okay, so large language models then take a different approach. They focus on language, and they basically leverage these networks to predict. And so you remember our output of predictions, and basically they, at a very simple level, they're going to have outputs of, let's say there are 100,000 words in English that we want to be able to predict, or pick the number that you want to have as output. Those are going to be the outputs, and you're going to send in the context and the input and whatever else you've got, and you're going to send in a certain number of previous words in order, and based on those, if you send the word there in with nothing else, maybe we get there is gets the highest weight, or there was maybe a little bit less, right? But based on its there are probably pretty high on the weights. But if you do say there are, then maybe you get there are many is the next logical. If there are many, maybe people's the most logical. And so it builds on these chaining based on input of, but again, it's a predictor. It's what's the most likely word to come next, given what we know and based on what it's trained on. And so then we move into transformers that are much more complicated in the way they go about that. They're built off of LLMs, but they use word sequencing at a deeper level, and a way to scale what that output is going to be, and to chain it together so that we end up spewing out a stream of the next words that come based on the inputs. And so the scale, if we go back to the polynomial experiment talking about, we were talking about fourth order or fifth order polynomials. GPT-4 has 1.76 trillion parameters. I mean, so fundamentally think of it like a polynomial. It's obviously more of a neural network, more complicated, but an unbelievable number of parameters. And in those parameters is distilled the information that it has, and in a way that allows it to be generative, and given kind of like that stable diffusion, given a lack of input to generate the next output. All right, I'm going to speed through this because I want to talk about a couple other things right at the end, and I still want to leave 5 or 10 minutes for questions. So what can they do well? Information retrieval, text generation, language translations, workflow automation, tutoring and education are certainly areas where, well, What it doesn't do well is it doesn't have a deep understanding. It has a reliance on training data, has a hard time handling ambiguity, context. We're going to get and risk of generating misleading information, hallucinating, right? I'm going to come back to those 2 points particularly. Privacy concerns, can't replace human judgment at this point. We'll see where we go with that. Let's see what we have next. So I'm going to skip through the fine-tuning components so we can take existing foundational data models like we've got Gemini, Claude, others. We can take those and we can distill them down to smaller units if they're publicly available, like Llama. We can fine-tune those models. And so in the generative AI company I'm working with, we often end up taking them, distilling them, and fine-tuning them because we don't have, we're not, put it this way, when we're asking whether a paper, scientific paper says whether a particular protein increases or decreases the expression of a gene and whether that leads to a disease or something, we don't need it to be able to recite Shakespeare, right? And so there's an incredible amount of information in these foundational models that isn't relevant to what we're doing. So sometimes we'll distill them down to a smaller set that's more particular to the function we're trying to do. It's faster and cheaper. And then we can actually fine tune that model. It's almost impossible to fine tune models the size of Gemini or OpenAI or those. They're just too big. You can't add enough new information to them to dent them at the scale that most companies can operate. But we can distill them down, we can fine tune them then, and we can get little better, cheaper results. Probably the most important approach that we take is retrieval augmented generation. So this, we add information at request time from other sources that helps guide the answer. We provide more context. We provide actual information about what we're trying to do in combination with what we're doing. Fundamentally, that can be done a number of different ways. You can run queries, get information out of a database, vector embedding, vector search, which is an area we could spend hours on in its own right. And then the other place that we go is connection to graph, so GraphRag, right, where we actually take graph databases, which are connected relationships of nodes. So between, think about it, a classic would be social networks, right? This person is a node, this person is a node, their relationship is a friend. And these triplets are entity, relationship, entity triplets. And then this person posted this article. And so I can get all the articles that my friends posted if I traverse the graph from my node through the friend relationship, through the posted to articles. And so you can traverse that and get back a list. Very good for relationship management. We use those extensively in combination with LLMs in order to do it. And then the other component of that is grounding, typically through something like an ontological knowledge base, but just a fancy way of saying a list of things we know to be true, right? And so if you think about a list of users in a social network, when someone puts a picture up or references a name, and if I said, hey, I'm friends with Doug, well, they're going to take I, and they're going to try to map that entity to John Jackson and an ID in our system. And they're going to try to look at Doug and maybe look at my friends and go, well, there's only one friend named Doug. It's probably Doug Baden, get his ID. And now we start to be able to work with this in a grounded way where we actually know what we're talking about. And now we can look up more information about Doug, more information about John. If this were a flight system, we could get my reservations. We can do all kinds of things with grounding. And one of the ways that we then can go from grounding is into queries, into relational databases or other data stores, or start to traverse graph databases and get information out. So all kinds of cool stuff. I think we may be out of time for running through vector embedding models. I highly encourage you to look in there. It's just incredibly cool as well, where you take semantic definitions of individual words and phrases and convert them into vectors. So like before when we looked at the handwriting sample, we converted it into 784 pixels from 0 to 1. In this case, at least the more recent versions of GPT kind of operate in like 1536 dimensional space with attributes like how much of How much of an animal is it? Is it fluffy? Is it dangerous? Is it spooky, right? And black gets spooky, but very low on animal. Aardvarks are high on animals, but not particularly spooky. And so this semantic relationship is actually incredibly powerful at certain volumes for getting information, correlated relational information out about information, basically by kind of using Pythagorean theorem in or other algorithms in multidimensional space. So I'm going to stop there and pause with 7 minutes left, 8 minutes left or so, and would love to open it up for questions. I'll even stop sharing here and see if I can see anybody's faces who wants to pop up. But hopefully that was helpful foundationally. Spend hours, days, weeks into practical application of that, how we get into orchestration, multi-agenic systems, kind of where the rubber meets the road. But the one takeaway as we're going through is, despite the hype and the true power and democratization of generative AI and these foundational models, don't forget about traditional models. They are much more cost effective when they're the right tool. What you're really solving for is when you run the processing, right? If you don't have a lot of training data, you probably need to use these generative models because you can give it one piece of input and get an answer out of it that may or may not be reasonable, subject to evaluation. But you're never going to train a more traditional ML system on a small amount of data. And so that's one of the major balancing acts. And then if you do end up, make sure that you're looking at grounding, make sure you're looking at how you evaluate, how you test even the outputs of these. And it's complicated because they're non-deterministic. You don't get the same answer all the time. So you can't run sort of traditional things. So what we end up doing is using LLMs as a judge to try to do that. And then we have to run through an evaluation process with human in the loop to evaluate and train our LLMs as a judge to be able to evaluate the non-deterministic output of LLM systems in order to have some reasonable confidence that what we're releasing into the wild with our customers is going to be within shooting distance of what we're trying to get as an answer. But whenever you can ground it, whenever you can use retrieval augmented generation as part of it, you get yourself a lot closer to confidence.
John Madan asks, any recommended eval frameworks for evaluating LLMs?
There are a bunch out there. I don't have a recommendation specifically because what we've found is that we end up writing them ourselves. And this isn't an enormous company. This is maybe 150 engineers or something. But the use cases that we've had at least are so specific that we end up writing our own evaluation frameworks internally, our own evaluation mechanisms, partly because we're just so reliant in this particular domain, especially with keeping scientists in the loop, that this is such a scientifically demanding domain and with a lot of ambiguity. Often the same word or expression means the same thing. And so we maybe do a little research and try to get back to you. Unfortunately, I don't have one off the top of my head because we write our own. That's in our last couple minutes.
Go ahead, Chris.
Just to help, there are some decent open source evaluation frameworks for the gentleman or lady who might have asked the question before, but you can look at things like maybe OpenAI's evals or a Hugging Face will have something for you as well if you're just looking to get started. We're trying to get some basic evaluation with your LLM. Just throw something out there.
Yeah, thank you very much. Yeah, I know they're out there. We unfortunately we've tried a few and didn't get a chance, or didn't get the results we needed with them. But that's probably more on us.
I think it's still an area where people are trying to figure out like what's an appropriate solution. But to your point, I think it's going to be very much each company's use case on how they need to evaluate those outputs that are coming, since it's obviously generative. So yeah, but there are some that are out there. Those are a few open source ones.
Perfect. Thank you. All right. Well, I thank you all for listening. Hopefully it was informative at some level, and look forward to diving into other conversations as we go forward.
Thank you, everyone. We'll have Travis, one of our colleagues, join next week, and then I'll be back on the docket in our 2 weeks after that, where we'll get into some approaches, how to evaluate these and apply these in your business, and measuring governance and maturity within your organization. So thank you for joining, and we've only got a few more in the series, and you guys have a great weekend.
Thanks, guys. It was good to see
See you
you.
in a couple of weeks, people.
Thank
Good to see you, Christopher. Take care.
Bye.